Hi everyone. So let's continue where we left off. So get to the fundamental theorem of arithmetic. Yeah. So the fundamental theorem of arithmetic. So every integer n except 0 and plus minus 1 is a product of primes, and this prime factorization is unique in the following sense. If we have two different representation for it using primes for n, then they must have the same size and they must be relabeling of each other. Then R is equal to S. So we have the same number of factors. Is the same. And after reordering, and relabeling, the Q's, then we have P1 is plus or minus Q1 and PR is plus or minus QS. Yeah, so let's prove it. So every integer has at least one prime factorization. So from the previous result. So all we have to do is show they have the same length, because if they are not, if they are the same length, then we could keep canceling things out and apply one of the previous corollary that we have. So let's see the details. Just primes, the thing is that primes don't so the main idea is really that primes, once you multiply them, they are atomic, so to speak, so they don't introduce new structures when you multiply them out. So that's the main core reason. So let's prove it. So by theorem 1.7, we have that n can be factored as products of primes. So that means that you have, let's say we have two different ways to represent n. So P1, P2 up to PR, which is equal to Q1, Q2 up to QS. So the reason I've written it down like that, because that tells us that P1 divides Q1 to QS. And so we have the following previous result, is that since P is prime, so which divides two numbers, then it must divide one of the numbers. So then by relabeling, so by relabeling and by relabeling things by previous and by previous result, what we must have is that P1 divides Q1, so we can replace P1 by Q1, but since P1 is prime, so that means that P1 is equal to plus or minus Q1. So then what we get is plus minus Q1, P2 up to PR is equal to Q1, Q2 up to QS, and then we can cancel Q1 from both sides, and we get that plus minus P2 to PR is equal to Q2 to QS. And we can do the same trick, and then we get, by applying the same trick, so by applying the same trick, we have that, so what do we have? If we apply the same trick, we get that P1 is equal to plus or minus Q1, and PR is equal to plus or minus QR. So we would be done if we had that R and S are equal to each other. So let's get a contradiction otherwise. So first, if R is bigger than S, then after S steps of the process above, then we get PS plus 1 is equal to PR is equal to 1, So this tells us that PR divides 1. So PR divides 1. So that means that PR is plus or minus 1. So, and that's impossible. So we arrive at a contradiction. So then, as PR is prime, so then that option cannot happen. And so we get that R is bigger than S cannot occur. So therefore, R cannot be bigger than S. And a similar contradiction for S is less than R by replacing the roles of P, R, and QS. Yeah, so let's show the following corollary. Corollary 1.9. So every integer n greater than 1 can be written in one and only one way, in the form n is equal to P1, P2, P3 to PR, where PI are positive primes, such that P1 is less than P2, which is less than PR. So we know that an n, if n is bigger than 1, we know that there is no negatives, and we can just put all the prime factors of n, which is guaranteed for n to be written as products of primes, but what we worked out before. And so we can put those things as a set, and we can just pick by the well-ordering axiom the minimum of this guy. This would be P1, and remove that, pick the minimum again, P2, and then we would have constructed the n to be like that, and by the minimality and well-ordering axiom, we get that representation is unique. So yeah, so that's the main core reason. So so let me discuss the following theorem. I'll discuss the main idea and then I'll close the video. So theorem 1.10. So it tells you that let n is bigger than 1 if n has no positive prime factor less than or equal to square root of n, then n is prime, then n is prime. So the main core reason for why this is true is actually if it has, so if it has, so let's see what's going on. So it says, the result says, if n has no positive prime factors less than or equal to the square root of n, then n is prime. So what do we want? So assume that the prime factors are bigger than the square root of n. So then you would be guaranteed that to find that your n is actually bigger than, you would actually find that n is bigger than n, where you get a contradiction. So the main point here is, if it has prime factors where the square root of n exists, then those prime factors, they multiply to n. So what this tells you is that the square root of n, it kind of is in between, is in the middle, in between the factors of n. So that's the main reason. So I'll talk about this a little more, but let me end the video here. I'll talk about the intuition a little more in the next video. See you guys.